everyone, and welcome to another Explainer. I'm absolutely thrilled you're tuning in today because we're going to tackle one of the most fascinating and kind of invisible challenges in modern technology. We're talking about the unimaginable massive wave of data that's being generated every second by the Internet of Things, or IoT. And more importantly, we're looking at the absolute architectural battle going on behind the scenes to process all of it. I mean, we've got billions of connected devices around the world constantly capturing data, but how does that data actually get processed fast enough to be useful? Well, today we are breaking down edge computing versus cloud computing.
Picture this for a second. You're cruising down the highway in your brand new self-driving car, right? Suddenly, an obstacle jumps out into the road. Your car needs to brake right now, immediately. Well, if your car operates entirely on a traditional cloud architecture, it has to take the data from its sensors, beam that data over a network to some server sitting in a data center 500 miles away, wait for that server to process the information, decide that yes, the car does indeed need to brake, and then send that command all the way back to your dashboard. In a life or death scenario, that just won't work. It is physically, literally too slow. In a scenario like that, your car only has about 10 milliseconds to react. 10 milliseconds. A traditional internet round trip is simply impossible within that tiny time frame. The sheer laws of physics and network latency just won't allow it. The data simply has way too far to travel.
Okay, let's dive into this and lay out our roadmap for solving this massive latency problem. We'll start with number 1, the cloud computing approach. 2, enter edge computing. 3, fog computing, which is the middle ground. 4, when to use which. And finally, 5, the hybrid future. Let's get right into it.
Section 1. The Cloud Computing Approach.
We're going to start with the foundation of the modern internet. This is the architecture most of us are super familiar with, the one we rely on every single day. So, what exactly is it when we're talking about IoT? Well, cloud computing is basically the process of sending all that device-generated data up to centralized remote servers over the internet for processing and long-term deep storage. Think about a smart thermostat in your house, right? It's updating its algorithms based on your weekly habits over time. Or maybe a car manufacturer collecting historical performance data from thousands of connected vehicles so they can design a better engine next year. That kind of data doesn't need to be processed instantly, so it's beamed up to the centralized cloud where massive computing power can just take its time crunching the numbers. And this brilliantly illustrates the unbelievable scale of the cloud. Look at iRobotic. They're the company that makes those robotic vacuums. They connect 30 million home cleaning robots globally, 30 million, and they use AWS, Amazon Web Services, to build, connect, and manage this massive global fleet. The cloud is exactly what makes it possible to orchestrate tens of millions of devices from one centralized location so efficiently. But here's the catch. The cloud isn't perfect for everything. On the pro side, you absolutely have massive scalability, cheap deep storage, and immense compute power. I mean, you can run incredibly heavy AI workloads in a massive cloud data center. But look at the cons. You've got latency delays, bandwidth limits, and a total dependency on having an active internet connection. If your internet goes down, or if you need a split-second physical reaction, like with our self-driving car earlier, the cloud's fatal flaw is exposed. For immediate physical actions, it is just too slow. Section 2. Enter edge computing. All right, this brings us to the really exciting part. This is the technology built specifically to solve that exact latency problem. Edge computing essentially flips the cloud model entirely on its head. It's a distributed framework that processes data locally, right at the source. That means the processing happens right on or directly next to the IoT device itself. So instead of sending the sensor data from that self-driving car 500 miles away, the car itself is the computer. It processes the data right there on the dashboard and makes the decision to brake instantly. The data stays completely local, no 500-mile round trip required. So the crucial point is that while Edge gives us the blazing speed we need, it definitely comes with its own set of rules. The pros are fantastic, right? Ultra-low latency, the ability to work entirely offline, and way better privacy and security because sensitive data never actually leaves the device. But the cons are very real. You've got limited local compute power and constrained storage. I mean, you literally cannot fit a massive AWS server rack inside a car dashboard or a portable medical monitor. Plus, managing all that local hardware out in the real physical world can get pretty costly. Even with those constraints, the applications are absolutely game-changing. Let's look at how Edge is driving immediate action across different industries right now. We obviously talked about autonomous vehicles, but in healthcare, Edge processing allows for remote patient monitoring while keeping all that highly sensitive data localized, which makes staying HIPAA compliant a whole lot easier. Financial institutions are using it for real-time, split-second fraud detection right at the point of sale. Volkswagen uses Edge services to connect data across 124 of their manufacturing plants to improve physical factory uptime. And AWS even offers something called the Snowball. It's literally a rugged, suitcase-sized edge device that you can just drop into disconnected, harsh environments to run local computing. How cool is that?
And guys, the scale of this shift is just staggering. Based on data from Statista, we are projected to have 40.6 billion IoT devices operating worldwide by 2034. That is more than double the projections for 2025. With the integration of Edge AI, where complex machine learning tasks actually happen directly on these tiny devices, this market is experiencing massive growth and moving far away from a total 100% reliance on the centralized cloud.
Section 3. Fog computing, the middle. So what happens when you have a task that is just too big for a single, small edge device, but still way too time-sensitive to send all the way to a distant cloud? Well, let's talk about a very specialized middle ground. This is known as fog computing. Think of it kind of like a bridge. It's an intermediate processing layer that adds extra compute power right between your local edge devices and that distant cloud. A great example from our sources is in telecommunications. Companies like Dish Network use this exact architecture to automate their 5G networks. They put computing resources right in local cell towers or regional hubs, that's the fog layer, so they can handle heavy local workloads with incredibly low latency, completely bypassing the need for a primary cloud data center hundreds of miles away.
Let's move to and see how this builds into a complete data journey. It's literally a three-step path. Step 1, your edge device, like that car or a factory sensor, generates the data and handles the immediate millisecond reactions locally. Step 2, that data flows up to a fog gateway. This is a local node or regional server that filters the data, basically throwing away the junk and processing the heavier local tasks. And finally, step 3. Only the most important long-term data gets sent all the way up to the cloud, the central server, for deep historical analytics. It is a highly efficient filtering system.
Section 4. When to use which? Now, what's really interesting about this matrix is seeing how developers actually decide where the data should live. If you're an engineer building an IoT system, you map it across three main things: speed, cost, and context. If you need batch processing, where speed isn't a huge deal, you're going to want the centralized cost efficiency and the deep historical context of the cloud. But if you need real-time millisecond speed for an immediate local action, you are absolutely going to pay the higher local hardware costs to deploy at the edge. It's this constant, delicate balancing act between these three pillars.
Section 5. The hybrid future. And that brings us to the plot twist derived from our sources today, and honestly, the reality of where this entire industry is heading. The title of our explainer today was Edge Computing versus Cloud Computing, but the truth is, that versus battle is a total myth. They are not competitors at all, they're partners. As enterprise hybrid environments keep evolving, the most powerful and resilient IoT ecosystems run on an infrastructure where both of these work seamlessly together. Think of it this way. The edge handles the reflexes, the immediate, localized physical actions, while the cloud handles the brain, the long-term learning, the heavy storage, and the deep analytics. You simply cannot have a smart, modern IoT infrastructure without both of them playing their distinct, crucial roles.
As Edge AI continues to mature, we are going to see incredible computing power pushed right into the palms of our hands, into the dashboards of our cars, and into the appliances in our homes. So I really want to leave you with this provocative thought. As this technology evolves, what immediate decisions in your own daily life will soon be processed locally instead of relying on the cloud? Thank you so much for joining me for this explainer. If you found this breakdown helpful and want to keep exploring the tech world with me, please drop a comment below with your thoughts, hit that subscribe button, and I will see you in the next one.